Hello, and welcome to Team 1's AAE 339 project video. In this video, we will be discussing the hypergolic lunar ascent vehicle engine that we designed based upon the Apollo missions. Our project studied the use of a hypergolic engine for a lunar ascent vehicle based off of the Apollo 11 mission, with the goal of creating a general-purpose propulsion system that is not just confined to a specific payload or vehicle, while still aiming to improve upon existing hypergolic systems. We primarily investigated hydrazine and its variants, as well as dinitrogen tetroxide as our main fuel sources, and weighed their benefits and fallbacks. In designing and researching a hypergolic engine, we aimed to create a propulsion system with the ability to have repeated and varying amounts of thrust as per the mission's requirements. Our design process had 5 components. First, we examined parameters on the moon. This included our vehicle's dry mass and launch mass under the lunar gravitational acceleration of 1.62 meters per second squared. Next, we examined the engine design itself. We chose a hypergolic engine for its reliable ignition, which is important on the lunar surface. After that, we discussed fuel and oxidizer properties. We decided on monomethylhydrazine and dinitrogen tetroxide. More on that in a minute. Next, we calculated the thrust required to take off the lunar surface. This ended up being about 14 kilonewtons. Finally, we discussed the limitations of our project. This mainly included research into the regulations surrounding the fuels we chose. Here, we examine a few different types of engines currently in use for space applications. We see a common trend in using monomethylhydrazine and dinitrogen tetroxide for the fuel and oxidizer. These propellants are pretty stable and can be stored for prolonged periods of time. They also have high energy densities and a high specific impulse, which means they produce more thrust per mass of propellant. That's why we decided to go with these options. Using NASA's chemical equilibrium analysis, various combinations of fuel and oxidizer can be tested to look at their effect on specific impulse. For a rocket problem, such as this, the chamber pressure was set to 13.79 bar. The fuel and oxidizers were set to MMH and dinitrogen tetroxide. Various oxidizer to fuel ratios and exit ratios were tested to determine the best potential configuration. Looking at the CEA outputs, several trends were noticed through different scenarios. In each case, the specific impulse increases as the area ratio increases. An oxidizer to fuel ratio of between 2 to 3 was ideal, and further CEA analysis showed that the specific impulse peaks around an oxidizer to fuel ratio of 2.25. This is the most ideal ratio for our lunar ascent vehicle. Based upon statistics from NASA's original Apollo missions, our report investigated the process and theory behind designing a new hypergolic engine. Starting with research into already existing hypergolic engines, we used the Apollo missions to determine the parameters of this engine's mission, including masses for each stage. Once the governing parameters were established, and knowing the general characteristics of this new engine, we compared the newly designed engine and the engine used on the Apollo missions. Notably, the hypergolic engine produced slightly less thrust, but boasted a greater specific impulse, with a lesser overall mass and a different nozzle configuration. This ultimately meant that our engine could meet the performance standards needed for its mission. While still theoretical, our newly designed engine is at the very least demonstrating that a lunar ascent vehicle could realistically be propelled by a hypergolic engine into orbit based upon past mission parameters. Additionally, implementing the new engine would allow for the removal of additional engine components, like an ignition source. This project merely encapsulated a fraction of the potential of hypergolic engines. The design itself could be improved with further research and testing, and as the field expands and more knowledge is garnered, perhaps someday the aerospace industry will see a greater implementation of hypergolic engines.